Hello everyone, today let's take a look at QP91, a basic Bernoulli question. In this question we have a quality control inspector who examines widgets for defects, and a widget is defective with probability P, and we let x equal 1 if the inspected widget is defective and 0 if it's not defective, so x is Bernoulli random variable. And in part A it's giving us that the probability is 0.3 of a defect, so we'll say P equals 0.3, and we want to find the expected value and variance of x, so let's first find the expected value. So the expected value of something is just the average value that you expect it to take in the long run. So this is as easy as it's going to get with a Bernoulli. We have a probability of 0.3 that there is a defect, and when there's a defect, x takes a value of 1. So 30% of the time, x will have a value of 1, and then the other 70% of the time, right, just 1 minus 0.3, we're going to have a defective widget, and in that case, x will take the value of 0. This is obviously equal to 0.3, which just means the average value of x for a given trial is going to be 0.3. Also, more generally, the expected value of any discrete random variable is just going to be equal to the sum over all the possible values that x could take times the probability that that event actually occurs. So in our case, for general P with the Bernoulli, well, x can only take values 0 and 1 if it's Bernoulli, so we're going to get this equation right here. This is the probability that x equals 1, right? The probability is defective, and then this is the probability that is not defective, which is just 1 minus P. So that tells us in this case for the Bernoulli, the expected value of x when we're given a general P is just equal to that probability. Okay, so now let's find the variance of x when P is equal to 0.3, and this is just a measure of spread. In our case, x can only actually take values 0 and 1, and we know that the average or expected value of x is 0.3. So the variance is just a measure of the difference between the mean and the actual values that x can take itself. So one thing we could do, if we wanted to find the average distance, we know x takes value 1 30% of the time, and we know x takes value 0 70% of the time. And then when x takes a value of 1, we have a distance between the mean of 0.7. So 30% of the time, we have a distance between the mean of 0.7, and then the other 70% of the time, when x takes value 0, we have a distance of 0.3. So if you were doing it that way, you'd get 0.21 plus 0.21, which would give you 0.42. So this is one measure of average distance, but it's actually not the variance. In this method, we're computing the distance between the mean and the values x can take using basically the absolute value between them. But in practice, this is not very useful because this formula that we're going to use is going to have an absolute value in it, which is not differentiable. And that's going to lead to a lot of problems later on. So instead of using the absolute value as the distance metric, instead in variance, we're going to use the squared difference between these. So what that looks like in practice would be take the value of x and we just subtract off the expected value of x, that would be 0.3 in this case, and then we just square it. That's going to be our distance metric. And then we're going to want to find the average over all of these distances. So basically we can take the expected value of this term inside here. So again, we want this term in here squared instead of absolute value, so it's going to be nice and differentiable. And also we don't want it to just be x minus the expected value of x without any absolute value or squaring, because then we could get negative values in here, and we want our variance to be always positive. So now let's actually calculate the expected value in our case when we had p equal to 0.3. Well, we know this distance here was 0.7, so the squared distance is going to be 0.49, and that happens 30% of the time. And then the other 70% of the time we get 0.3 distance, and we have to square that, so we get 0.09. So that's going to be equal to 0.21, so that tells us that our average squared distance is 0.21 in this case. Okay, so that was the variance when p is equal to 0.3, but now let's think about it for general p. So now in our case, x can only take values 0 and 1, so we take those values and we subtract off the expected value, which we found in part A was equal to p, and we square that distance term for the reasons we talked about earlier, and we weight each one of these by the probability that x takes that value. So when you expand out that summation, it looks like this. The probability that x equals 1 was equal to p, and the probability that x equals 0 was equal to 1 minus p. So we get that this term over here is equal to p times 1 minus p all squared plus 1 minus p times this right here, which is just going to be p squared. And then we can factor out a p times 1 minus p, and then for this term right here, we're just going to have 1 minus p, and for this term over here, we're just going to have p. So these are going to cancel right here, and we're going to get that the variance is just equal to p times 1 minus p. So this is the variance of x for a Bernoulli. And then quick sanity check, if we plug in 0.3, which we already calculated, we get 0.7 times 0.3, which again is 0.21, so yes, it makes sense. Okay, so now in part B, it's asking us what values of p minimize this variance right here. So p times 1 minus p, that's equal to p minus p squared. That function is just going to look like an upside down parabola, right? We know that p is a probability, so it can only take values within the range of 0 to 1. So since the function of variance looks like an upside down parabola in this case, the minimum values that it's going to take are going to occur at our endpoints 0 and 1. So if we plug in p equals 0 over here, we get that the variance of x is equal to 0 as well, right? We should have 0 minus 0. And if we plug in p equals 1, well then we get the variance of x is equal to 1 minus 1 squared, which is 0 again. So the values of p that minimize the variance are 0 and 1. And that makes sense because if p equals 0, then the widget is never defective, and if p equals 1, then the widget is always defective, and in either case we would expect a variance of 0. Now in part C, let's find the value of p that maximizes the variance. This one's also really simple just by looking at the function of variance, because we know that these points right here pass through the x-axis. This is when p equals 0, and this right here is when p equals 1. So then the peak of the parabola is obviously just going to be halfway between these 2 points, so it should be at 1/2. When we plug 1/2 into our function for variance, we get 1/2 minus 1/4, which is equal to 1/4, so that's the maximum possible variance that we could get. Could also solve this just by taking the derivative and finding the critical points, in which case we'd get 1 minus 2p, and then set that equal to 0, we get p equals 1/2, right? And also our second derivative would be equal to -2, so when we evaluate this at the point 1/2, obviously it's still going to be equal to -2. So at this point right here, the rate of change of the slope is going to be -2, which tells us that this is a local maximum. So the value of p that maximizes the variance is 1/2, which also makes sense because that's right in between the two values that x can take. And this is obviously the maximum level of uncertainty that we could have about whether or not an item is defective, right? If it's 50-50.